In a distributed environment, network failures are a mathematical certainty. System design is the practice of choosing exactly how an architecture will compromise when those failures occur. Take this foundational question. In a distributed system that must tolerate network partitions, the P in CAP, the theorem states an architect must make a trade-off between which two guarantees? A, latency and throughput, B, consistency and availability, C, relational and non-relational structures, or D, horizontal and vertical scaling. The correct answer is B. The CAP theorem dictates that when a network partition severs communication between nodes, the system forces a choice. You can either ensure every remaining node has perfectly consistent data by shutting down access, or you can keep the system available, risking the return of stale data. The other options describe different concepts entirely. Latency and throughput are addressed by the Pascal theorem. SQL and NoSQL are database paradigms, and scaling up or out is a deployment strategy, not a theoretical limit on data guarantees. Understanding CAP allows an engineer to decide in advance whether an application should serve outdated information or simply refuse to serve any data at all during a crisis. Consider this scenario. Which load balancing algorithm is required if user sessions, like a shopping cart, are stored directly in a server's local memory for the duration of a visit? A, round robin, B, least connections, C, source IP hash, or D, random allocation? The answer is C. Source IP hashing takes the client's IP address and mathematically maps it to a specific server. This ensures that as long as the user's IP remains the same, every one of their requests hits the exact same machine, preserving their local session state. The alternatives fail this requirement. If you use round robin or least connections, the user's second request will likely land on a different server. Since their cart data was stored in the memory of the first server, the session is lost. When an architecture relies on stateful local memory, network routing must be deterministic. Without it, adding more servers will actively break the user experience. In the data layer, caching strategies define who moves the data. In which strategy does the application layer request data from the cache, and upon a miss, the application itself fetches from the database and updates the cache? A, write through, B, cache aside, C, write behind, or D, read through? It's B, the cache aside pattern. The distinction is in the orchestration. In a read-through cache, the cache provider handles the fetch. In cache aside, your application code takes the lead. It checks the cache, identifies a miss, fetches the data from the database, and loads it into the cache. Now, look at database partitioning. Which sharding strategy is most susceptible to the hotspot problem, where a single shard receives massive traffic compared to others? A, hash-based, B, range-based, C, directory-based, or D, consistent hashing? The correct answer is B. If you partition by a continuous range, such as user registration dates, the shard handling today's registrations will receive nearly all your new write traffic. This creates a bottleneck on a single machine, while older shards remain underutilized. Strategies like hash-based sharding avoid this by algorithmically distributing data based on a key, ensuring load is balanced across the entire cluster. Both caching and sharding require an engineer to map out how data will accumulate over time. Without that foresight, optimizations eventually create choke points. Let's apply this. When an e-commerce checkout completes, the system must trigger an email, update inventory, and notify shipping. Which messaging pattern fits this requirement? Pause the video, select your answer, and try to explain why the other three fail. The answer is C, publish subscribe. The checkout service publishes a single order completed event to a topic. The email, inventory, and shipping services each subscribe to that topic, receiving the message independently and asynchronously. The alternatives create single points of failure. In a point-to-point queue, once the inventory service reads the order, the message disappears, so the other services never see it. Synchronous RPC is even riskier. If the shipping service is down, the entire checkout process fails. Publish-subscribe architectures isolate your components. This prevents a localized service failure from causing a system-wide outage. Finally, let's look at the system boundary. What is the primary structural purpose of an API gateway? Option C is correct. It acts as a single entry point, abstracting back-end complexity by handling routing, authorization, and rate limiting before requests hit your internal services. Option B is a common pitfall. Executing heavy business logic or orchestrating complex transactions inside the gateway transforms a lean routing layer into a monolithic bottleneck. Resilient systems are built on three principles: enforcing strict network boundaries, managing state efficiently, and decoupling components so they can scale and fail independently. You've just covered 6 of the most important trade-offs in software architecture. Take a screenshot of this guide. Mastering these rules will help you design systems that survive the pressures of production.